without further ado, let me introduce our speaker for today. So Mathias Larrouturou is a mechanical engineer from McGill University in Montreal, and he's specialized in aerospace propulsion. Currently, he's enrolled in a master's degree in mechanical engineering, and he participated in a variety of space-related research projects already, ranging from food production from deep space missions. So between you and me, if you have the chance to talk to him later, just ask him about his crickets. He has some very interesting things to tell about them. But he also worked with laser thermal propulsion up to plasma physics and advanced propulsion. Over the past 4 years, Mathias dedicated his efforts to the development of several propulsion technologies, with a particular focus on harnessing in-space energy sources and mass flows. And his most recent work includes the development of plasma surfing applied to fast round trip within the solar system, and the design of a parabolic electrostatic nozzle for a fission rocket. And that's exactly what he will be talking to us today. So,
thank you. So, hello everybody. Thank you for TNG for having me today. And I'll be talking for the next 45 minutes about the work I've been doing in my lab at McGill University. And I'll be talking about plasma surfing within the solar system and hopefully beyond. So, first I want to give a quick introduction, mainly to give you a feel of the context and what has been done in the community, what has been done in the field. So, the first thing you have to understand when we're talking about propulsion system is the most basic propulsion system is a rocket. We've all seen them. They're pretty common nowadays. And they're all limited by a single equation. It's the rocket equation, also called the Chodovsky equation for the man who invented it. And we really don't like this equation in aerospace. It really is the worst equation we could ever dream of. For a very simple reason, you're in the logarithm regime. So essentially, what this equation tells you is what is the velocity gain you have for a certain amount of fuel and for a certain exhaust velocity. And you can double the amount of fuel, you will not double the final velocity you'll have, because you've got this logarithm inside of your equation. And so as you increase the amount of fuel you have ever decreasing return on investment. So the gain in velocity decreases the more you add fuel. And so at McGill, we're thinking that, okay, there's bound to be a way to get out of this equation. We have, and we need, if we want to unlock the solar system and other solar systems, we need to find a way out, because rockets are fundamentally limited. And so we can start with the basic principles. What is a propulsion system? And if you conserve and do not violate any laws of the universe, if you conserve energy and momentum, you need two things. You need a reaction mass, and you need something to accelerate that mass. For a chemical rocket, well, the chemical reaction is your energy source, and the products of that reaction are the reaction mass. And so all of the work in aerospace field has been centered around rockets. And so in the particular case of rockets, you have an internal reaction mass and an internal energy source. So everything is contained within your rocket. And that's what fundamentally limits you and brings you to the Chodovsky equation. It does not matter how you do your energy source, what kind of propellant you have, what kind of energy source you use. If you have an internal reaction mass and an internal energy source, you are a rocket. It does not matter. The details do not matter. And so we're thinking, and it is my goal today, to convince you that we should look into systems that are not internal reaction mass and internal energy source. And I'll try to convince you over the next 45 minutes that not only does it yield very interesting and innovative technologies, it also gives you interesting trajectories and performances that, because they are not rockets, those propulsion systems destroy rockets in the classical sense of it. trajectories are just not comparable anymore. Okay, so first things first, the simplest externally powered propulsion system, we actually know it quite well. It's a solar sail. You deploy this incredibly thin mirror, roughly the thickness of a human hair, and due to the photon pressure from the sun, you can accelerate your spacecraft or your satellite, and you do not expend energy, you just have to produce this very thin mirror and deploy it. And that's already an external reaction mass and an external energy source propulsion system. But there's a catch. The accelerations you get are only as good as the scale of your system. So if you want to have large acceleration, you need a very, very large mirror. The issue is, beyond a certain point, just increasing the radius of your mirror gives you more mass than added acceleration. And so beyond this point, increasing the size of your mirror actually slows you down. And so the idea, you can kind of pin it down. You're limited by the mass of the mirror, you're limited by the material properties. If you want to start very close to the sun, then you have to make sure your mirror doesn't melt. And the issue is very simple. You have a small area of interaction, and it's your mirror. And in the end, you cannot go beyond a millimeter per second squared of acceleration. It's great for attitude control. It's great for rovers if you want to launch them to Mars or bring them back to Earth. But for humans, that means like years in deep space. It's absolutely unfeasible. So the next step in the community was to say, okay, what if we get rid of the physical mirror, and instead of having this thin mirror, I have a magnetic field? Because in our solar system, we have something called the solar wind. It's this flow of charged particle that is emitted by the sun, and you can interact with it. It's a plasma. You can use electromagnetic interaction to do it. And so the first MagSail was invented by in the 70s, and it uses just magnetic interaction. You scatter particles from the solar wind, and you can actually produce drag, just like how a parachute produces drag in the wind. You produce drag within the solar wind. But there's, again, fundamental limitations. You need superconducting cable to have nice current densities. The radius is 30 kilometers, so the mass are just huge. We're talking about just in the realm of 10 tons just for that cable, and we're not even considering the cooling system and everything that's required. But it's still a step forward, because now the acceleration are on the scale of a centimeter per second squared, which is 10 times better than the solar sail. And if you know a bit about electromagnetism and how human technologies have evolved, it's very hard to control large currents. When we're talking about like hundreds of kiloamps, the hardware becomes physically big. And so the space and mass inefficiencies tell you probably to get rid of the magnetic field. And so John Noonan proposed this idea, okay, if it's easier to control voltage than current, we'll go down this road. And so instead of having this thick superconducting cable, I have this micron thick wire, and I electrostatically charge them. I just turn up the voltage incredibly high. And this you can produce within a lab with inexpensive material. You can produce kilovolts, if not megavolts, incredibly easily. And so the idea is the same. Instead of having a magnetic field that scatters particle, you have an electric field that scatters particle. The issue is that now the plasma is kind of fighting you, because there's this phenomenon called Debye shielding. It's essentially, if you put an electric field in a plasma, you'll attract oppositely charged particles. And in plasma theory, we call this a sheaf. And so from very close, yes, you see your electric field, but from very far, you see your source, and next to it, a cloud of oppositely charged particles, this sheaf. And so they cancel each other. And so from the far field, you do not see anything. You do not feel the electrostatic field. And that's the limiting factor. The way to get around this, don't have a single cable, have hundreds, if not thousands of them, and that's what you have. I'll try to point it. That's what you have. You can see here the different cables that are repelling the different charges from the solar wind. And so the accelerations are on the scale of a centimeter per second squared, but you still need that 10 kilometer radius of area of interaction. So now let's go into the meat of it. So if you're giving a talk, we'll probably tell you, every prof will tell you, focus on the big idea. The issue in this talk is there's 4 big ideas, and I'm not even kidding. And we really tried in our labs, we've tried to talk about this concept for a long time, and it's incredibly hard to summarize it, because it's technology built upon other technologies, and it's been like this for the past 20 years. And so there's 4 big ideas. We'll focus mainly on the first one and the 2 last one. The first one is the plasma magnet. After there was the Q drive, and then plasma surfing, which is my research, and dynamic soaring. Okay, so let's start with plasma magnet. I will not try to teach plasma physics, but I'll give you a couple of hints as to what is happening. So the functioning principle of this is, if having a physical coil is killing us, could we just get rid of it? And the idea is to induce a current into the plasma. We've been inducing 20 kiloamps currents in 5 centimeter cube plasma since the 70s. Could we do something similar in space? And so this idea is, if yes, how do we do it? And could we essentially remove this physical coil that we have, this 30 kilometer coil that we have, and have a much smaller system that is generating large scale currents? And so the way we do it is, I'll explain in much more detail later, but you have 2 coils that generate a rotating magnetic field. Maxwell tells you, well, a rotating magnetic field is a current. This current will expand due to self-induced Lorentz force and inflate like a bubble, like a balloon. And because of that, you have this amplification process, and now we can have accelerations that are on the scale of a meter or 0.1 meter per second squared. So we're 10 times to 100 times better than the best MagSails that we could ever dream of producing. And so the main advantage here is you reduce the scale by a factor of 1,000. You went from 10 to 20 kilometers to 10 to 20 meters of scale. And so the mass goes down that much too. Okay, so let's talk about the actual, is it me? No, okay, that seems to be good. Let's talk about how this thing works. So you have 2 coils, and you drive 2 sinusoidal currents in those coils, and they're 90 degrees out of phase. So what happens is that you have one coil that is energized when the other one is at 0, and 90 degrees of phase later, it's inversed, and you can create this nice rotating magnetic field. And the idea here is to induce a current into the plasma, and you can make the very simple case that electrons are incredibly lighter compared to ions, so we'll just induce the current with the electrons, and it will be much simpler. This puts a couple conditions on our system. We need to operate beyond a certain frequency, which is the ion cyclotron frequency. I'll get into that in a second. And you need to make sure that your electrons are very mobile. And so in the end, what those 2 conditions mean is you want the ions in the solar wind to be as immobile as possible. For a very simple reason, they're incredibly massive, they have huge inertia, they're hard to move, they don't induce current well, it's a huge loss. It's a huge energy loss. And for the exact opposite reason, you want your electrons to be incredibly mobile, just essentially to have a nice efficiency. And so if we continue forward, a rotating magnetic field, you use Maxwell, a rotating a time-varying magnetic field induces an electric field, and this electric field will accelerate your particles and your electrons. And so this electric field, at some point you will reach maximum velocity, and this maximum velocity is just the equilibrium between the collision, that scatter momentum between the ions and the electrons, and the accelerating force of your electric field. And so I will not go into the detail of the equation, but you can very easily compute the induced current. And what you happen to have is this, it's not an exact simulation, it got rendered to explain it. But essentially you have those nice electron rings that start spiraling outside of your system, and you have this nice current, and you could very easily say, well, again, we have a rotating we have a current, Maxwell tells us it's simply a magnetic field. And yes, those electrons that spiral out act like a MagSail, like any current loop, and they generate a magnetic field. And so essentially you could argue, well, we're back to the MagSail. Why do we care? We just generated a magnetic field. I have those two chords. It's more complex than the MagSail. Why do we care? Well, we care for a very simple fact. First of all, our system is 10 to 20 meters in diameter, not 10 to 20 kilometers in diameter. Second thing, those electron rings will expand. There's something called self-induced Lorentz force. So imagine a balloon that we try to inflate. This balloon will expand, and it will expand up to the point where the pressure that I inputted into the balloon from my lungs is equal to the outside pressure. And here we'll have the same thing. The magnetic pressure is the inside pressure of our balloon, and the external pressure is the dynamic pressure of the wind. And this is what will confine our electrons. And so we'll inflate, slowly but surely, this gigantic plasma bubble, this gigantic magnetic bubble, and we have an amplification process, because the larger those electron rings become, the more solar wind they stop, the more they stop the solar wind, the more particle we can start trapping into this plasma bubble. And so you have a feedback loop. So you start stopping electron, those electrons make your current higher, that increase in current allows you to inflate slightly more, and you'll reach an equilibrium, just like our balloon expands until all of the pressures equalizes. Well, here our plasma bubble will inflate until the magnetic pressure and the dynamic pressure perfectly equilibrates. And so the idea is, again, why do we really care about it? And we care for one simple reason. Those currents, we did not have to pay any mass for them. I did not have to bring a physical coil into space to have those currents. And so the idea is now I have an incredibly mass efficient system. And the beauty of it is that there's a lot of advantages that will come. One of them is, as those electron rings expand, you can imagine that they are equivalent to infinitesimal concentric MagSails that are spread all over your area of interaction. And so what that means is that at any point in your plasma bubble, you generate magnetic field. You have a current loop that is acting like a MagSail, generates its magnetic field. And so the magnetic field you generate does not fall as 1 over r squared. Why do we care? Well, that means that we can generate a very intense field much further than any physical coil, because typical electromagnetic coils, the fields fall off as 1 over r squared. So we're already beating the MagSail by a significant margin in the area of interaction, in the scale of our system, and in the intensity of the fields. And that's why the plasma magnet is so interesting for us, because it has a lot of advantages. And essentially here you have the little animations I showed you. It's mainly for explanation. And here you have the actual trajectory. It's much more complex. The equilibrium is, the electron rings are in equilibrium in 3D. It's much more complex to explain, but essentially it's the exact same principle as before. And maybe you didn't understand me at all. Maybe you said, okay, well, I don't get plasma physics at all. It's not my thing. I don't get math. But I can actually, give me 5 minutes and I'll show you why we care about all of this. If you have a system like this, what you truly care about is how good your parachute is, how good you have, how good your amplification process is, so how much energy do I have to pay and how much energy do I get out of it. And that's what this equation here at the bottom is. On the left side, we have the power intercepted from the solar wind, and this corresponds to the power associated with the drag force in the solar wind. And on the left side, on the right side, this PRMF is the energy I need to provide to my coils to make this rotating magnetic field. And first of all, it's a very interesting equation because everything is linear. So now we're out of this logarithm regime. If I double my input energy, I double the output energy. And we have the output on the left side, the input on the right side, and in between we have this fudge factor. And if we have an amplification process, this is essentially the factor that determines how good our amplification process is, how efficient it is. And at minimum, you would want it to be 1. In our case, it's not 1, it's 7,000. So if I input 1 kilojoule of energy and I have a 10-meter radius plasma magnet, now I have 7 megajoule of energy, sorry. And that's very interesting because suddenly you can multiply the forces you have and you can multiply the energy you have. And you do not violate any energy. It's an amplification process. You do not violate any fundamental laws of the universe. It's an amplification process. And the big idea here is that you still need to pay at some point the energy to drive those rotating magnetic fields, but you get 7,000 times more energy than you inputted. And that is very interesting when you compare it to rockets, because now I can have much higher forces. And so maybe you're like, okay, this Canadian guy is presenting this totally fluke, charlatan concept. So there's a couple of things we can take from fusion theory, from plasma theory, to prove to us that, okay, we're not fooling ourselves. We're not looking at this weird regime of plasma physics that theoretically works, but practically does not work at all. And so the first thing you can do is borrow from plasma physics and fusion theory, and it's called the confinement time. It's how much time can you control a plasma, can you confine a plasma within a region of space solely due to a magnetic field. And if you input the different values for this plasma magnet, we're on the scale of decades. So that means, okay, this metric is not telling us that we're totally chasing a mirage. It's telling us, okay, we're not getting blown by the solar wind. It could work. Now you could say, okay, maybe you can confine it, but maybe you're in such a high energy, current, intense regime that, like, yes, the forces work out in your favor, but you have this incredibly impossible system to sustain. And okay, what is the total current? Plasma theory tells you a nice, neat equation that you can use, very well established in the literature. Almost every physics and fusion people has to derive this equation at some point on their homework, so we know it's the good formula. And the total amperage is only 9 kiloamps. Okay, that's clearly not saying that we are chasing a mirage again. Okay, so what is the energy in that field? Well, only 84 kilojoules. Okay, that's not bad. What is 84 kilojoules? Well, any car outside this conference hall that is like post-2000 has a car battery with 1 megajoule of energy in it. So we're 10 times less than that. And we're interacting over kilometers squared, hundreds of kilometers squared. So now you might be asking yourself, okay, how does that work out? I have an incredibly large confinement time. I only have 9 kiloamps of total current and 84 kilojoule of energy. How can I interact with the solar wind, which is like a supersonic flow flowing at 400 kilometers a second with 9 kiloamps when the MagSail needed 200 kiloamps? And there's a nice explanation to it. And the idea is, because we induce a current directly into the plasma, and we can imagine that every electron is a very small MagSail, and that all of this compiles into an infinite amount of concentric MagSails, we can say that because we have this infinite number of MagSail, we can turn the current way down, because now I do not need to generate this very intense field. I just barely need to generate enough magnetic field to have this nice magnetic pressure, which is in equilibrium with the dynamic pressure of the wind. And so that's the trick. You need very few energy because it kind of self-spreads out and self-optimizes itself to be in equilibrium and have the lowest amount of energy required to be in equilibrium. And so, if I didn't lose you up to that point, there is a next step forward. But just before that, theory can only get you this far. It was actually tested in the lab, so we kind of know that it works. And it was tested in the 2000 by Slav. And we actually saw the plasma magnet expand. So like here, as you go from left to right, the dynamic pressure of the wind is decreased. And you can see that the blue region in the little window here is slowly expanding as we turn down the dynamic pressure. So we saw that plasma bubble inflate. And you cannot see it here, but essentially during the experiments, the system moved up and down as they turned on and off the jet from the solar wind plasma gun. And so why do we care about the plasma magnet? Can we have a nice, tangible way of saying how good it is? And the answer is yes. There's a proposed mission as a technology demonstrator. It's called the YOVI mission. It's a 25-day flyby of Jupiter. So you launch from Earth, and 25 days later, you're at Jupiter. If you're not in the aerospace field, it's unheard of. It is leagues above anything else. And there was a mission that was launched a couple of months ago called the JUICE mission. It's the European Space Agency launched a mission to Jupiter. And it's been, I think, 4 months now, and it has done 1.5% of the trip. You could launch in 8 years and still reach Jupiter faster with the plasma magnet. So that's why we care. It is just that much more powerful and efficient than any other classical chemical rocket. Okay, so now the big idea. So the next step forward was, okay, we have this plasma magnet, seems to work, been tested in the lab. It's pretty much incredible already, but can we build upon this? Can we make it even better? And at a conceptual level, you can argue that if you have a drag device, you can extract energy. If you can modulate this drag, if you can increase or decrease the amount of drag you produce, if you can inflate or deflate your parachute as you want, you can extract energy from your flow. And that's the functioning principle of every simple anemometer that you make with spoons and build with a 5-year-old. And essentially, by modulating this drag, you extract energy. You have a higher drag surface in one direction than in the other, and you generate torque. You have a generator at the bottom of your anemometer. You've got power out of it. And so Greason in 2019 proposed this idea that we could do the same thing in space. Take 2 plasma magnets, and just like how an engine strokes the gases, the combustion gases, well, we can stroke the solar wind. And if we produce more drag on the way out than on the way in, you can extract power out of it. And so that's actually what you do. You have 2 plasma magnets, so you inflate the bubble upstream, and you slowly but surely turn down the current in your coils, and you turn up the current in the second plasma magnet downstream, and you'll have this moving magnetic field which will go from the first plasma magnet to the second one. And you have your collection antenna in between the two, and you'll be able to extract power out of this. And so that was a considerable step forward, because now not only do we have a parachute, we have our anemometer. We have a way to extract power from the solar wind at a large scale, because again, those electrons current are not, the scale of those currents is not determined by the physical size of your system, but by the equilibrium of the magnetic and dynamic pressure. And so the big idea at McGill was, okay, we have this energy extraction device, what can we do with it? And the idea of the Q drive, I'll go back for a sec, was use this energy to expel propellant. So you have an external energy source, internal reaction mass. And our idea at McGill was, okay, could we make it fully external? Could we have external reaction mass, external power source? And the idea is, I'll go through the physics very quickly, is you have your spacecraft. You can do this analysis any way you want, yields the exact same thing. But you have your spacecraft here, and you have 2 particles going at the velocity of the wind, and you decelerate one in the direction of the flow. In our case, this is the x direction. And you can extract energy from this deceleration. There's a drag associated with that, of course, but you have power. And so, because energy goes as v squared, but forces go as v, you can play a trick on the wind, and you can use that energy to accelerate the wind in the perpendicular direction. And this is exactly what an aerodynamist would call lift. And so you essentially are starting to act exactly like a wing. We are not in the parachute. We cannot only produce a force in the direction of the wind anymore. We can produce a perpendicular direction. And if you go through the physics, and I'll ask you to believe me for now, you have that the lift-to-drag ratio, which is like the fundamental equation that determines how performant a wing is equal to 2 times the velocity of the wind divided by the perpendicular acceleration you give it. And again, that's very interesting for us because everything's linear. We're out of the Stokowski equation, we're out of the logarithm regime, and we have this fully linear equation. And so if I decrease by 2, the perpendicular acceleration I give the fluid, well, now I can double the lift-to-drag ratio. And if you have a bit of background in aerodynamics or in hypersonics, this is exactly the first model of the hypersonic flat plate. You can also derive this equation if you consider 2 mass streams or if you have 2 rotors. Just like how the Stokowski equation does not care about the details, this equation, you can derive it. It does not care about the details. And so how do we do that? Well, this is by no means the final implementation. It is not optimized. There are better ways to do every step of the way. But it proves that it can be achieved. And so to extract power, you use the plasma magnet array, just like for the Cube drive. And to generate lift, to accelerate the fluid perpendicularly, you use plasma waves. And why do you want plasma waves? Well, there are a couple of reasons for that. One of them is the solar wind is incredibly thin. To give you an idea, in the air around us, there's 10 to the 19 particles per centimeter cube. In the solar wind, there's 5. So there's 18 orders of magnitude between Earth's density and the solar wind's density. And so if you have an extremely diffuse medium, you only have one trick you can play. You need an incredibly large area of interaction. And again, if we do not want to pay for this mass, for this large system, we need plasma to help us. And there's only one way you can do this. It's through plasma waves. And so I'll not try to teach at 9 a.m. plasma physics and plasma waves even less, but there's a couple of quantities you can use. It's called the Poynting vector. It's just the amount of energy per unit of area. And the equation we really care about is this one, because again, fully linear, and it tells us that the group velocity, which is the perpendicular acceleration, or if you want to think of it as a quanta, it's the velocity at which the energy quanta travels through the medium. And in this case, it tells us that if we divide by 2, the perpendicular acceleration or the group velocity, well, we'll double the lifting force we'll generate. And that's, again, very interesting because it comes back to the lift-to-drag ratio. And so we kind of know that we're on the right track. Nothing is killing us for now. And we can start looking at possible plasma waves, and there's a bunch of plasma waves. One of them is called the X wave, there's the R wave, the Alvin wave. Every different physics community has different name for them. It's a pain in the ass to go through the different names they have, but there's a couple here that you can use. And the group velocity is determined by the dispersion relation. It's how the media responds to the disturbances you generate. And you can very quickly have here the group velocity in the y-axis and the frequency of the wave in the x-axis, and it's through the warm plasma approximation. So you take all finite amount of finite temperatures into account, and at the Earth you can generate a lift-to-drag ratio of 15, and much further at the termination shock, which is the boundary of our solar system, you have a lift-to-drag ratio that is well above 50. And so we have one last condition to meet, is that we do not want those waves to spread omnidirectionally, because otherwise there's no net force. The flux is everywhere the same. You have absolutely nothing, you have no force. So we want a compact antenna design that's efficient, that is capable of sending unidirectional waves. And actually there are a couple designs that can do so. Ruskalp proposed one of those antennas. You can see that the energy quanta in one direction is much higher than in the other, and so essentially that means the antenna is producing a unidirectional wave. So why am I here? Well, in 2017, Spencer Lisenby proposed and presented at TNG his dynamic soaring research, and the idea is that you can use a glider to reach transonic speeds. You can reach Mach 0.85, Mach 0.9, and you use no propeller, you use no onboard propellant, And if you listen to what I said over the last 30 minutes, it's kind of what we want in space, to have no onboard propellants and no onboard energy source. And so it's kind of the right track. And that was a huge inspiration for us, because he was capable of not only demonstrating on Earth, but he was capable of showing that it worked incredibly well, because he reached Mach 0.85 without any issue. So just before we talk about how it works and how dynamic soaring can actually work in space, we just have to talk about a couple of things. So when we talk about lift, drag, we're used to talking about lift and drag in the context of airplanes. And sadly, it's a bit a specific case, because airplanes, the velocities are all in the same plane. The apparent wind velocity and the velocity in the ground reference frame are in the same plane, and so your lifting force cannot accelerate you forward or backwards, because it's almost perfectly perpendicular to you. And so the idea is, what if I could have a forward component to my lift? Could I use this lift to accelerate me forward? And to do this, you need to be always at an angle with respect to the wind. Sadly, if you have a single static uniform wind, you cannot do that for a very simple reason. The wind pushes you towards equilibrium, same direction and same velocity as the wind. So you need two winds. Okay, but how does that work? Well, if you cannot do it at steady state, you only have one card, transient effects, and you need to ensure that all the way around your trajectory, you have a non-90-degree angle between your lift and your velocity. And that's how you can have a forward component. And so what you do is that over one part of the trajectory, your lift is always slightly forward, continuously accelerating you. And so you accelerate over this first part of the trajectory, and we need a way to, if we're here, we need a way to come back here and reappear in the wind at an angle. And there's only one way to do that. If you stay within the same wind region, you'll accelerate on the first part as much as you decelerate on the second part. You gain no velocity. But if you have a slower wind, now you can accelerate forward more than you lost energy on the second part of the trajectory. And that's how you do it. So there's two analytical limitations you can derive. I will not go through them with you, but sadly for time. But you can derive the maximum velocity you can reach and the maximum velocity gain you can have over a single cycle. And why do we care? Well, because in space, regions of different wind speed, we have a lot of them. Three of them are given here: the fast and slow solar wind, the termination shock, which is at the outreach, at the outer part of our solar system, and we can even use planetary magnetosphere that act like giant obstacles for the solar wind. And so you have wind shear, you have differences in wind speed, you have shocks, and you can surf and dynamically soar on them. And so to check all of that, we did a couple of numerical investigations, and we found that the theory matched the numerical simulation within less than 2%. So we knew that we were not breaking any fundamental laws of the universe. We could, from base principle and first principle, derive those and make them work, and that dynamic soaring was legitimate and not a fluke, not a mathematical trick. And so, sadly, in the previous case, in the previous analysis, it was a planar shock. So it was essentially the spacecraft was moving in a plane. The solar wind and our solar system is very much not a plane, so now you have curvature effects that come in. And giving you the punchline very quickly, at the end of 1.6 years, we can reach 2% of c, 2% of speed light, and at that speed, ironically, the solar system is incredibly small. The solar gravity is incredibly weak. You've reached the escape velocity of our solar system months ago. And so you're essentially just trying to, you're fighting against your velocity to stick to the wind, to stick to the surfaces and the structures you want to dynamically soar on. And so at that point, you do not want the highest efficiency at the lowest angle. You don't want the perfect trajectory. You want the highest wind gradients, and that's at 90 degrees. You just go straight into the wind gradients, and you take the largest delta V as possible, because it's just so hard to stick to the structures you're surfing on. And so that is at the outer part of our solar system. It's at 100 AU and 120 AUs, so it's very far. It's 100 times the distance between the Earth and the Sun. And so if you want to do it at a much closer distance, so at 1 AU, for instance, you don't even have to reach 2% C to be above escape velocity. Within 2 weeks, you're already so fast. You're at 0.5% C. You're already so fast, you cannot stick to the structures. So you end up, actually, dynamic soaring actually decelerates you because you have more losses than you have velocity gains over your first part of your trajectory. And so now you might actually just do a single turn, a single cycle, and just phew, go out of the Earth's orbit. And so next question is, okay, dynamic soaring is incredible. Okay, can we do something a bit less far out? Could we do something much closer? Could we reach Mars? And the answer is yes, we can do it. If you can reach 2% C, you can probably reach Mars. And so the idea is you can reach Mars in 49 days. And once you're below the 2-month mark to Mars, you essentially have unlocked the solar system. From a propulsive standpoint and from a trajectory standpoint, you're capable of generating such velocity and forces that you can reach any part of the solar system relatively in decent times. And so here you have the 6-month architecture. It's kind of like the standard to estimate how good a propulsion system is. There's not really a lot of systems that can do 6-month missions to Mars. Even Artemis currently is fighting on 3 years, but they cannot do 6 months at all. So this is one way of saying that propulsive system, whether you use this the implementation I propose or not, has incredible potential in terms of what it can do within the inner solar system. So, in terms of conclusions, there's a couple of conclusions we can say. That the big answer here from the talk is you can achieve high lift-to-drag ratio in the solar system and in the solar wind. Plasma waves seems to be the most viable answer to generating the lifting force. And thanks to that, and thanks to dynamic soaring, you can reach 2% C in 1.6 years or 0.5% of C in a mere 2 weeks. And the last thing is within the solar system, you can do a 6-month architecture. All of those are a great conclusion, but if I may leave you with one conclusion, is that there exists working propulsion system that at the physical level do not violate any laws of the universe and that are fundamentally different from any rockets and are fundamentally different from the propulsion system we've had up to this point. Thank you very much for listening to me.
Thank you very much.
You're welcome.
Now it's question time. Are there any questions in the audience?
So merci beaucoup for your crazy thoughts and realistic statements. I have a question regarding how plasma physicists get their intuition. Because, for example, I have no intuition about the electromagnetic fields. But sometimes if you discover something, you need a hunch, you need a direction. But where do the hunches, the intuition, come from the mathematical equations or from playing with these ideas for many years? But where do the intuitions and the ideas come from, please?
So I'm going to give you a very unsatisfying answer, both, sadly. And so before the plasma magnet, there was this idea called M2P2. And it's the idea that instead of trapping particles from the solar wind, you initiate your own plasma. So you could, for example, inject within your magnetic field argon or any gas that you want to ionize. And it's from this that the plasma magnet birthed. And because the engineers on it, and mostly Sloth, from their experiment with the M2P2 project realized, wait, you don't even need to inject plasma up to that point. You're already, the plasma is already helping you that much. You just use the solar wind as your plasma, as the plasma into which you induce the current. And to answer your question, it is incredibly hard. I'm a mechanical engineer. I'm not a plasma physicist. Building the intuition of plasma is incredibly hard, and if you actually go to a plasma physicist and ask them, okay, could you surf on the solar wind? Could you actually produce the lifting force within the solar wind? They'll tell you, we don't know. Because physicists and engineers don't ask the exact same type of questions. Physicists tend to ask the question of what is the state of that plasma? How does it behave? And engineers tend to ask the question of what can we do? What could it be done? And so the intuition is not even the same in both fields. The intuition you're trying to build is not the same, and it's incredibly hard to build one. I'm at the same point as you, as building this intuition is very hard. I hope I answered your question.
There are no questions on Slack yet, so we can go ahead here.
I think there's a lot of questions in the audience.
Hi, thanks for this really cool talk. You talked about this mission to Jupiter in 25 days. So what's keeping you? Like, what will it cost? How much time to build it?
So I'm not going to give you a timeline for the very simple reason that that's not how science works. If you say, in 10 years I'm going to put a man on Mars, you put your credibility and your rigor onto the plate. You say, okay, I'm putting my credibility, I'm going to do it. It's incredibly hard. The technologies have to do their own journey. You cannot force it. But the plasma magnet, in the case of the plasma magnet, every analysis that could be done has been done. Every experiment that could be done has been done. Every numerical simulation that could be done has been done. And so the next step is testing it in space. The issue is that for this UV mission, yes, 25 days to Jupiter is incredible, but there is a physical scale to that plasma magnet. The plasma magnet scales very well up in size, but it scales very badly down in size, and so it's very hard to test it on like a CubeSat or on a cheap satellite that you could launch or do. There have been a couple of satellites that have used essentially fundraising to actually be launched. The issue is the UV mission, you need a 16U CubeSat, and it's in the millions of dollars, and it's above what you can do with fundraising. You need someone to take it on as a real project, as part of a business plan to actually do it. But for now, what is keeping us? Mostly money and resources. But yes, we could theoretically build it. We have a working design. It could be, of course, iterated over and improved upon. But we have a design. But yeah, we're essentially waiting for the time to actually test it in space first. Thank you very much. I hope I answered your question. No. So in regards of the physical appearance, so the implementation I've showed you is, as I said, by no means final, is by no means optimized. I'm just going to say things before answering. So the way we extract power of the plasma magnet, one analogy, I didn't have the time to put in the slides, but one analogy is, imagine you have a parachute, and this parachute is linked to a spool of cable. And that spool of cable, the axis is linked to an electric generator. Essentially what the plasma magnet array is you throw this parachute, you wait for the parachute to deploy and pull the tether and to unspool that spool of cables you have, and you extract power from that. And once the spool is over, you essentially collapse the parachute, rewind the spool, and that's how you have losses over that, but of course, a compressed parachute has much lower drag than a deployed one. There's a reason why windmills do not look like that. It's inefficient, it's mass inefficient, you need someone to respool the system. And so what I'm trying to say is there's bound to be a better way to do it. There's bound to be a better way of extracting power from the solar wind. One of that option, for example, is electrodynamic tethers. They've been tested in space. They've been tested with the American Space Shuttle a couple of decades ago. The energy densities do not work in favor of that in the solar wind, but if we can improve on that and make it work, it could be a much more viable option. Similarly, Langmuir probes are a much more viable option if we can make them work and optimize them for power extraction. What I'm essentially saying is the physical appearance will be determined by what technology you use, and it's by no means final. It's by no means the last iteration you'll see of this spacecraft. And so yeah, so the physical appearance is up to debate, essentially. I think there's a couple of questions.
By now, there's also a question online, which says 0.5% of the speed of light in 2 weeks implies a structure able to sustain incredibly high forces. Is there any material candidate that makes the intuition feasible?
So that's a very good question. So Spencer Lazenby, the man that inspired our talk, his dynamic soaring gliders actually pull hundreds of Gs. And when they mess up the trajectory, that thing explodes and shatters. And so you probably do not want that for your spacecraft if you have human in it. So there are bound to be, yes, material constraint that you have to take into account. There'll be a point where you'll have to say, okay, we're accelerating too fast, we have to stop. We have to turn our systems down, and we have to stop dynamically soaring. Yes, absolutely, you'll have material constraint to take care of. It's much too advanced to even consider material constraint at this point. There's still a lot of the physics that has to be worked out, a lot of the plasma physics that has to be improved upon. I hope this answers the person's question.
Okay, so because of the time constraint and we don't want to cut the next talk, there's room for one last question.
Hi, thanks a lot for being here for us. I have just a quick follow-up question to the question that was there before. You mentioned the costs of sending this spacecraft of sort, or this propeller to space. What would be the cost to actually build the thing, the propeller? Because apart from the cost of sending it there to work.
The cost of the spacecraft? Yeah. I'm not a big fan of giving timelines, budgets, simply because when you finish your talk and you say, we can reach 2% C in 1.6 years, you're already asking a lot from the audience in terms of credibility. And so if you put even more, you ask even more credibility by saying, oh, you can do it for 10 million in 10 years, you might start raising a couple of eyebrows, and a couple of people might have left the audience by that point if I had said that. So sadly, I will not answer your question. In terms of simply scientific rigor, I do not want to answer that question.
Okay, I was just wondering if there are any exotic materials or anything that's like involved.
No, so, okay, so this I can answer. The entire approach we have in our lab is to use very well understood and established physics and technologies. So like inducing a current in the plasma has been done since the 70s. One thing we're essentially saying here is technologically we could have built this thing during the Apollo program without any issue. A couple, but not major ones. And so you can use standard material. There might be a point where you say, okay, we're reaching the material limitations. We have to stop. Just like how a solar sail, you cannot be infinitely close to the sun because at some point your mirror will melt. Well, at some point you might have to say, okay, we reach 1.5% C. Our system, we're seeing micro cracks. We're seeing the carbon fiber is not responding well. We'll stop. And that's how you'll determine to, okay, we'll do it with standard materials, but we'll have to take into account those material constraints. You're welcome. Thank you very much.